Okay, so now we're on to part 2 of section 1.2, graphs of equations. And we're going to talk about symmetry and the equation of circles. Uh, to start with symmetry, we have a few graphs for you to look at. The first one that we're going to talk about is x-axis symmetry, right? And if you notice on this graph, we have our x and y axes, and we're symmetric about the x-axis. Now, granted, I didn't draw the best of pictures, but technically what we're saying is that this line is like a mirror image of this line, right? When we're crossing the x-axis, say any point on this graph should have an opposite y point on this side, right? Notice that when we're talking about symmetry about the x-axis, the only thing changing in our points is the sign of our y value. I forgot to put that in parentheses on there, right? We're changing the signs of our y value. Our points would be the same. If this was 1, 4, this would be 1, -4, right? So the only thing that changes with x-axis symmetry, right? For x-axis symmetry, the only thing that changes is the sign of y, right? And we'll know that something has x-axis symmetry based on that. When we're talking about symmetry about the y-axis, you guys have seen this before because this is quadratics. This is a terrible drawing. Clearly, I made this side bigger than this side. But for the sake of argument, let's pretend that I drew this well and that this side is the same size as this side. If you notice, the only thing changing on here is we have negative x, positive y over here, and positive x, negative y, and positive x, positive y on this side, right? The only thing changing in a y-axis symmetry would be the sign of our x value, right? So for y-axis symmetry, the only thing that changes is the sign of our x value, right? So for x-axis symmetry, we change the sign of y, right? For y-axis symmetry, it changes the sign of x, right? If it's symmetric, there would be, for every negative x, there would be a corresponding positive x where the y is the same. For y symmetry, for every negative y, for every x value, there would be a positive y that's the same as the negative y, right? You'd have 2 points for both x, one positive, one negative. It would be the same. Symmetry about the origin changes both signs, right? Origin symmetry, if I have an xy value, for every positive xy value I have the opposite sign, right? Think of that in terms of opposites, right? Because we could be going from negative to positive. I could have a point that was, say, 4, -2, and for it to be symmetric, I would also have to have a point that is -4, +2. If that makes sense, it would change both sides, right? So it's not necessarily going from positive to negative, because if I have a positive and a negative, I'm changing the signs of both. And that's how I would show symmetry. Symmetry would say that for every xy I have, I also have negative x, negative y, right? We can plug in whatever numbers we want for those and know that we have to have the opposite. So there's some graphical tests for symmetry and there's algebraic tests for symmetry. We're going to write down the rules for both of those. I can actually make this piece of paper turn. I don't want to do it all in red pen. So the graphical test, we're going to have a couple of little charts here on what you could do. This is very note-taking, but you'll get the gist of it. You should be taking notes while you're doing these videos anyways. Graphical tests for symmetry, right? Just like before, we're going to have 3 steps in this one. Step number 1, a graph is symmetric with respect to the x-axis. Symmetric with respect to the x-axis. If whenever we have an xy, point xy on the graph, we also have x negative y on the graph. All right, it's exactly what we just went over, right? When we have x-axis symmetry, it means that for every xy, we also have an x negative y, right? So if I have a point 1, 3, I also have to have a point 1, negative 3, right? If I have a point, say, -3, -2, I also have to have a point -3, +2, right? That y value sign is going to change, right? So that's our rule number 1. Rule number 2, right? So that would be how we determine whether something is symmetric about the x-axis. When we want to know if something is symmetric with respect to the y-axis, a graph is symmetric with respect to the y-axis when or if, whenever xy is on the graph Can you guess this one? Negative x, y is also on the graph, right? So we have xy. We would also have to have negative xy for it to be symmetric with respect to the y-axis, or symmetric about the y-axis, or different ways you'll hear it said, right? So given these same points like I had above, if I want to prove symmetry about the y-axis, if I had the points 1, 3, I would also have to have the point -1, 3. In that same respect, if I had the point -3, -2, I would also have to have the point opposite that on our x, which would be +3, -2. Right? So now we've learned how to show symmetry about the x-axis, symmetry about the y-axis, and the last one we have to show is symmetry in respect to the origin, right? So a graph, we can just write this over again. A graph is symmetric with respect to the origin. The origin is 0, 0. It's that spot on the graph where everything starts and ends. So something to be symmetric about the origin means it's within respect to that 0, 0 point on a graph. If, whenever, xy is on the graph, -x, -y is also on the graph, right? So if I have a point xy, for it to be symmetric, I would also have to have the point -x, -y. And that would be for every point on the graph, right? So if we went back to the point 1, 3, for it to be symmetric, it would also, for it to be symmetric about the origin, it would also have to have the point -1, -3, right? And if I had the point -3, -2, I would also have to have the point 3, 2, right? Because it would have to be true for every point within that graph. So that would be how we test for something graphically. You could look at it and see. Now there are algebraic tests for symmetry as well. And they work somewhat similarly. So we're going to talk about how to find them algebraically. So I'm going to go way back to the top of the paper here. The algebraic test for symmetry, algebraic, E-R-A-I-C. So for the algebraic test for symmetry, we're going to have to do the same thing. It will be respect to the x-axis, respect to the y-axis, and respect to the origin, right? So we're also going to have 3 of these. So if I have number 1, symmetric with respect to the x-axis, when we replace y with -y, we yield an equivalent equation. So what does that mean? It means that if in the equation I can replace y with negative y, we're going to have the same value to that equation, which makes sense, right? Because what we're saying is that x doesn't change, right? And if we look at our graphically, when we were talking about it graphically, right, it's saying that we can change the y to a negative and x would still be 1, right? That it wouldn't change the value of x. Everything would stay the same, right? It's just that we would represent both points, right? Here, I changed my y to the opposite, but my x's stayed the same. And that would be true for every point on the graph, right? When we're talking about symmetry, with respect to the y-axis, then it's the opposite. We can replace x with negative x, right? When we replace x with negative x, we yield an equivalent equation. Right? It's the same thing we were doing before, right? I could look at this point, right? It's saying that if I have x and y and I replace x with a negative x, I'm going to get the same y, right? But we're talking about it in terms of an equation now. It's algebraic instead of graphic. We're not dealing with just points, right? But what we're saying is that whatever I put in for 1, if I replace 1 with negative 1, my y, my outcome is going to be the same, right? If I replace negative 3 with 3, I'm still going to yield negative 2 on both of those, right? So if I'm changing the value, the sign of the value of my x, I'm going to yield the same y. That's ultimately what we're saying with that. So you saw how that changed for x, and you saw how it changed in respect to y. So the origin is going to say, hey, if I replace both of these with their opposite, I'm still going to yield the same equivalent equation, right? It's still going to take me to the same place, right? So um, so graph of an equation, symmetry, with respect to the origin, right? Before we did x, then we did y. When we replace x with negative x and y with negative y, we yield an equivalent equation. And can't spell, I'm a math teacher. Equivalent equation. All right, so it's the same thing. It's just really another way of stating it, right? We're stating it more numerically instead of stating it using graphs, looking for points on graphs, right? Because we're not looking at it in terms of points, we're looking at it more in terms of equations themselves, right? So testing for symmetry, let's look at that. when we are testing for symmetry,